became an obsession for William.
Welcome to our star party this evening. This evening's star party has a special guest speaker, Garima Singh, who will be talking to us about direct imaging of exoplanets, which essentially translates into taking family portraits of our extrasolar systems. The two main topics that will be introduced are adoptive optics, which like the art of reshaping the star planet light, and coronagraphy, which is the art of blocking the starlight, which we direct image use to address the above, like those other issues. Welcome, Garima. I personally am always very curious how astronomers study exoplanets, so I'm really looking forward to your talk. But before we begin, I just want to take a moment to center our attention on the land that our observatory is located on. We are so grateful to work, collaborate, and learn on the traditional lands of the Wasanic peoples, whom have been the custodians of this land long before the arrival of Europeans. We respect the continued connections with the past, present, and future in the ongoing relationships with the Indigenous peoples within the community, as we share with those peoples a historical relationship with the night sky. I, of course, encourage you to just take a moment and think about the peoples on whose land you currently occupy if you're joining us from Canada. Some of the flow for this evening, I'm just going to go over a few housekeeping things. So we've got a number of parts up for you tonight. So if at any point you have a question, if you're joining us on Zoom or on YouTube, please just put the question into the chat, and then we will feed the questions at kind of appropriate times. There will be an Ask an Astronomer section this evening. So if your question is not answered right away, it could be that we're just holding it until the Ask an Astronomer section. And then we are going to have Ben Dorman and Jason Beeman for that section to answer your questions there. So come up with some great questions. They like to be stumped. We're going to have What's Up in the Sky with Dawn. And then we're going to have Dennis Crabtree tell us a few interesting, new interesting things as well. And then, of course, we have our EAA group. And I have just told you all of those things completely out of order, so it'll be a bit of a surprise which order they come to you in. I want to also ask you to please mark your calendar. We have a couple star parties coming up. We have a star party. The next star party will be on April 16th. And the following one will be for International Astronomy Day on May 7th. I also want to give a little bit of a teaser that we are going to be launching a little bit of a prize giveaway next week. And it will be for images of the moon. However you do with that, I know I have personally tried to take images of the moon a number of times through a telescope. It's not as easy as it would seem for the average, amateur astronomer. So if you start to get your images of the moon ready, we will post that to our website on Monday. And with that, I'm going to turn it over to Dawn Moffat for What's Up in the Sky.
Okay, thanks, Amy. And I'm going to start by sharing my screen here, but first we're just going to discuss a few things about just general astronomy right now. So as you know, spring begins tomorrow at 8:33 a.m. Pacific Daylight Time. And at that time, the sunset will be 7:26 p.m. and astronomical twilight will end at 9:12 p.m. So with the change in time, suddenly darkness leaps to a much later hour in the evening. And full moon happened yesterday, so we still get pretty much a full moon, a waning gibbous. And also note that we actually passed the point of the split between equal day and night on Thursday. So it's not actually happening tomorrow. And that's actually known as equilux. And so equinox is tomorrow, but there's actually going to be about 10 minutes more daylight tomorrow than the nighttime. And so part of the reason is due to refraction. So the sun pokes its disk above the horizon a little earlier at sunrise and sets a little bit later than it would be expected if there was no air surrounding the Earth. And we also have to consider the definition of sunrise and sunset. So it's not the center of the solar disk. It's really when that first little bit pokes above the horizon in the morning and when the last little bit goes down. So there's both the definition and the refraction that account for the definition. And so another thing to consider is where the sunrise and sunset happen on the equinox. And so you would think that it'd be due east and due west, but because we're seeing the sun a little bit higher than we might otherwise expect, it's not at 90 degrees and 270 degrees. It's actually at 89 and 271. So they're both out by about a degree. And so that's, again, due to the refraction. So, so you can imagine it kind of sliding up in the morning and just sort of going up a little bit higher and sneaking in. So for the March skies, I think what I'd like to do is focus a little bit on the Hyades star cluster, and we can see it up here in the middle of the screen, and I'm going to attempt to zoom in a little bit here. And it's part of the constellation Taurus the Bull, and it has that very familiar shape that you can see there. And you can actually, an easy way to find it, of course, is to use the belt stars in Orion, and they more or less point towards the star cluster. And it's estimated to be about 625 million years old and has a mass of about 400 times the sun. And it's about 153 light years away and is about 10 light years in diameter, more or less, and making it quite large in the sky, about 7 times the size of the full moon. So, and it has a noticeable V shape, as we've already mentioned. And you should remember that Aldebaran is actually not a member of it. It's actually a star that just happens to lie in the line of sight, and it's about half the distance, which also accounts in part for why it's a little bit brighter than the stars that you would see in the Hyades star cluster. So if it was twice the distance, it would be about a quarter of the brightness, and so it would just look like one of the stars in the cluster. So also note that the Pleiades are over here. And it turns out that the Hyades and the Pleiades are actually roughly the same physical size. And it's just owing to the greater distance of the Pleiades that it looks so much smaller. So it's about 3 times the distance, and so it looks roughly 1/3 of the size. And since we're talking a little bit about exoplanets, actually quite a bit about exoplanets tonight, I thought I'd just point out a few stars that you can see in the nighttime sky right now that actually have known to have planets around them. And one of them is this star right here, and I'll just click on it, and it's called Oculus, which is a great name, and that's because it's one of the eyes of Taurus the Bull. It's the other eye, the brighter eye being Aldebaran. And just going to refer to my notes here because I don't have all of this memorized, of course, but it actually has has a planet that's about 8 times the mass of Jupiter. And we can find another star over here in Canis Majoris, the big dog. And if I can click on the right star, hopefully I'll click on the right one. And that's not it. It's, let's see if it's this one right here. That's it right there. It's 7 Canis Majoris, and that star has a planet twice the mass of Jupiter, and also one that's a little bit less than the mass of Jupiter. So that's a little bit harder to find because it's a slightly fainter star and it's lower down in the sky. And I'm just going to zoom out here a little bit, and we're going to look up at Gemini, the twins. And don't worry, I'm going to post a video a little bit later that helps you find all of these, so you can stop taking notes. I know you're all taking notes right now, of course. But right down here, underneath Castor, you can find a star that is Tau Geminorum, and that actually has a a planet that's 20 times the mass of Jupiter, and it's in an orbit that's roughly the same size as that of Earth. And finally, we're going to look at one more, which is actually circumpolar. And I'm going to zoom out for this and see if I can flip around without messing this up too much. And it's actually the brightest star in the bowl of the Little Dipper. And so this is also called Kochab. And so this is, that has a star that's roughly, a planet that's roughly 6 times the mass of Jupiter. So as we'll learn tonight, these planets are all over the place, but you can have a little fun and look around in the nighttime sky and identify some of the bright stars that have planets going around them. So I'm just going to click off here a little bit and zoom out. Oop, maybe I should zoom in a little bit. And just talk a little bit about the, oops. See, I joked earlier that I'm going to stumble a bit. That's kind of my job here tonight, is to make a few mistakes. And so I'm just going to actually change the time so that it's in the morning. And I'm going to zoom out a little bit. Oops. Let's try that again. Just bear with me. Well, I think I'm going to skip the technical part here. In the morning sky, you can actually see that there's a tight grouping of Jupiter and Saturn in the morning sky, and they'll also be joined by Venus and Mercury soon as well. So you can look for those down in the southwestern part of the sky in the morning. So with that, I think I'd just like to point out that we do have a lot of exoplanet material, if you're interested in that sort of thing, and our Exo Explorations part of the Center of the Universe website, which we created for schools a couple of years ago. And it's aimed at mostly at the grade 6 curriculum, but it's open to everybody. And I just want to mention one more thing that that happened. There's a fairly large, fairly noteworthy collision that happened about a couple of weeks ago. It was on March 11th, and there was an asteroid chunk about the size of a small car that collided with the Earth, apparently just north of Iceland. And it's variously been described as being the size of a grand piano or half the size of a giraffe. There's some very colorful descriptions of its size out there. But it was actually identified by a Hungarian astronomer about 2 hours before impact. And so this kind of raised awareness for this sort of thing. And this kind of collision happens fairly frequently. There's a fairly large collision about once a year between the Earth's atmosphere and an incoming body. And there is even, there's a fairly large one that happened in December of 2018 that happened over the Bering Sea that had an impact energy of about 10 Hiroshima bombs. And there is a much bigger one that happened, as you might recall, back in 2013 over Russia. And that's the Chelyabinsk meteor, if I'm pronouncing it correctly. And that had an explosive energy of about 500 kilotons, about 30 kilometers up in the atmosphere. And so that was captured on many dash cameras. And people at first wondered why so many people got video of it, but it turns out that many people have dash cameras in Russia because they don't trust the authorities and they like to record what actually happened if they got in an accident to use as evidence. Nevertheless, a lot of dash cameras in cars picked that up. It was momentarily brighter than the sun. Apparently nobody suffered permanent eye injury, but there were a lot of injuries due to glass fragments as windows broke. And there was about 100,000 homes that had windows that were broken, and about 7,000 buildings that suffered some sort of structural damage. So that was a very noteworthy one, and no one was killed, fortunately, but these events do point out that we have to keep monitoring what's out there for our own safety. So with that, I think I'll pass it back to you, Amy and Calvin.
Hi. So I wanted to mention that we are, of course, we're a membership-based organization. So if you are interested in becoming a member, you can find that on our website, which is centeroftheuniverse.org. You can also follow us on social media to find any kind of fun stuff that we're up to, and we're at Friends DAO on everything, Instagram, YouTube as well, and Facebook. So we'd love to have you follow us, and then you'll know every time we, post a new video, have a star party. There's other videos that get posted in between as well. I am going to just introduce Dennis Crabtree first. Dennis is a great friend to the FDAO, and he is definitely the historian on the Hill. So, Dennis, you have some interesting things to tell us?
Yeah, thank you for that introduction, Amy. I'm not as old as the Hill. I'll just point that out. Um, but yeah, so we all know, or people might know, that the observatory opened on May 6, 1918. So by this point in time, 100 years ago, the observatory was in more or less normal operation. Uh, bit just before COVID hit, we discovered the monthly reports that Plaskett sent to Ottawa, recording on the work done by each of the people on staff and some other information about observing conditions, etc. So people can find those reports on the web if they want by Googling for Plaskett reports. That's Plaskett. And believe they start in November 1921 and go through sometime in 1933. So next month I'll report on the April work, which includes a big discovery. For March, it was a sort of a poor weather month 100 years ago, but they got some spectra of stars and other things. It was a bit of a sad month for Dr. Plaskett. His mother died. She was living in Osoyoos, where two of her other children lived, Robert, a son, and Annie, a daughter. So they were both living in Osoyoos as well, and I believe the mother was living with her daughter. But anyway, she died in March of 1922. There are still Plaskett relatives that live up in Osoyoos, by the way. Another thing that Plaskett did during this month was he gave a talk in New Westminster at St. Mary's Parish Hall in New Westminster in Sapperton area. And his one of his other brothers, Frank Plaskett, was the Reverend Canon Frank Plaskett, had been rector at the church since 1912. And he continued being pastor at the church until he died, I believe, in 1946. So he had a long tenure there at that church. And there was a stained glass window in the church dedicated to their mother.
Recording in progress.
Now, I'll just add a personal note. I just recently discovered that I had a second cousin, once removed, that was married in 1942 by the Reverend Frank Plaskett. So I have a cousin that was actually married by the brother of John Stanley Plaskett. So a little personal connection to the Plaskett family. And I think that's the little snippet from history for this month. I'll pass it back to Amy.
Hi. Sorry, okay. I am going to introduce our speaker. So our speaker for tonight, like I said earlier, is Garima Singh. Garima is a postdoctoral fellow at the Hertzberg Astronomy and Astrophysics Building.
Amy, I think Ben is
sorry.
with you now.
Sorry, I wasn't sure if he had just came in.
Just in the nick of time.
Okay.
Ben, you can take it away if you want to unmute.
No, I'm sorry. I just got home. We had an internet failure at the center of the universe building, so I just got in. Sorry, Amy, please continue.
Oh, okay. So Garima is specialized in developing instruments that take direct images of exoplanets. She completed her PhD in 2015 in a collaboration between the Subaru Telescope in Hawaii and Paris Observatory in France. Before moving to Canada a year ago, she worked as a postdoctoral fellow with NASA's Jet Propulsion Laboratory and with Paris Observatory, where she continued improving the wavefront sensing capability of exoplanet imaging instruments. Garima, welcome.
Good evening. Thank you so much for this wonderful introduction, and thank you for having me. Let me first share my screen. Can you all see my screen and hear me well?
Yes.
Okay, great. All right, good evening. So this evening, I would like to talk to you about exoplanets and how to take their direct images. This is a patch of the sky in the universe, and here you see at least 10,000 galaxies. So universe is filled with galaxies. It has trillions and trillions of galaxies, and galaxies are filled with billions and billions of stars. And if we focus on one such galaxy, our galaxy, Milky Way, Milky Way galaxy has 300 to 400 billion of stars. Our galaxy is 100,000 light years across, and 1 light year is 9.5 trillion kilometers. And sun and our solar system is 200 million light years away from the center of the Milky Way galaxy. So if we focus on the sun, we see a solar system. We have 8 planets, and I like to show this image because it kind of shows that we have basically visited mostly all of these planets. We have explored all of them. And so if we go back to the image of the Milky Way and the sun, NASA statistics says that each dot that you see in the night sky has at least one planet orbiting it. So planets that orbit star other than the sun are called exoplanets. And so each dot that you see in the night sky has at least one planet orbiting it. So as of today, we know roughly 5,000 confirmed exoplanets, and roughly 9,000 of them are candidates, which means that we are not sure if they are planets or brown dwarfs or low mass stars. We don't know yet, but these planets, we know that they are exoplanets, and these are planets in our neighborhood in our own Milky Way galaxy. So the question is, why do we care about exoplanets? And I think one of the most fascinating question of one of the most fascinating question is, are we alone? Is there life outside of planet Earth? So if we just focus only on our solar system, we do have some bodies which potentially could harbor life. So for example, Titan, which is Saturn's moon, has lakes and rivers of not water, but methane and ethane. Europa, which is Jupiter's moon, has ocean of liquid water under the icy surface. Enceladus, which is another one of Saturn's moon, it ejects plumes of salt water in space. So this is an image taken by a Cassini-Huygens spacecraft. And so there are hydrothermal activity going in the subsurface ocean of this moon. So yes, the question about life outside of, other than Earth, is the biggest question. But we astronomers are also curious about other questions, such as we want to understand how planets form and evolve, and how unique is our solar system. Planets like Earth, the habitable planet, are these common? We want to study the physical and chemical composition of these planets, and we want to study exoplanets just because we are curious. So here I want to tell you, how do we find exoplanets? And they are categorized, these techniques are categorized in two ways. One is indirect technique, and the other one is direct technique. So when we talk about indirect techniques, we basically study the influence of a planet on its star. We don't see the planet with our eyes. We just try to monitor we monitor the star to see if there is a planet around it or not. So I'm gonna discuss only two such techniques. One is called radial velocity. So in radial velocity, what happens is, like, if you have a planet orbiting a star, it's gonna make the star wobble, because when two bodies, they orbit around each other, the whole system orbit around their center of mass. So if a planet around a star is going to make the star wobble, and you can actually study the spectrum of the light emitted from the star, and you can study the periodic shift of the spectrum of the star. So if the star is it's moving away from us, the spectrum is going to shift to red wavelengths, and if it's approaching us, it's going to shift to blue wavelengths. So you can study the Doppler shift of the light coming from the star. So using this technique, we have found roughly 915 exoplanets. So this one, so the very first exoplanet that was discovered around a main sequence star was through radial velocity, and that was in 1995. And that planet was hot Jupiter. It was called hot Jupiter because it was the size of that planet was the same size as Jupiter, and it was completing one orbit around its star, I think, in 4 days. So it was a big giant planet like Jupiter, very close to a star. So it's very hot. So that's why, well, it's one of the category of an exoplanet, hot Jupiter. So radial velocity is one of the most successful methods to find planets. Second one is transit. So what happens in transit? If you have planets orbiting a star, and if the whole system is aligned, it's the edge-on system aligned with your line of sight. And if a planet is moving in front of the star, you can actually study the light curve of the star. And if the planet is moving in front of the star, you can see the dip in the light curve. And just by studying this light curve, you can figure out how many planets are there, how far they are, and how big they are. So with the radial velocity, you get the lower limit on the mass of the planet. With the transit method, you can figure out the size of the planet, and so both of these techniques are complementing each other. So if you observe a star planet system, if you observe a planet through these both of these techniques, you can get the information, lower limit on mass and the size of the planet. And once you have these two information, you can get the density of the planet. And once you have the density, you can figure out if it's a rocky planet or a gas giant or something in between. So these two, with transit, we have found roughly 3,700 exoplanets, and mostly through Kepler Space Telescope. So these two techniques are really exoplanet finding machines. The other technique, which is called direct imaging, this is something that I work on, is where you actually get to see the real images of exoplanets. So a planet is roughly 1,000 to 10 billion times fainter than its star. So obviously, when you're looking at a star planet system, it's impossible to see visually a planet around a star. So you need to block the light of the star. So that's what it's showing in this video, where you block the light of the star and then the faint signal from the planet appears in the background. So I would like to show you how a real extrasolar system looks like. So here what you see, these 4 dots are real exoplanets. All of these videos before that I showed a simulation. This one is a real video coming from Keck telescope. Keck is a 10-meter class telescope on the summit of Mauna Kea in Hawaii. And they have You may have seen this video before. This is the data collected, I think, over 8 to 10 period of 8 to 10 years. And what you see is 4 planets orbiting the star, which is roughly 116 parsec away, or maybe closer than that. And 1 parsec is 3.6 light years. So anyways, these planets that you see, these 4 planets, they are giant planets. We call them extrasolar, sorry, we call them extra gas giant planet. So these planets are at least 5 times bigger than Jupiter, and they are lying very far away from their stars. So, so I basically work on instruments, instruments that are used to take such images. So from now onward, I'm just gonna talk about, well, actually, no. So as I said, today, we know roughly 5,000 exoplanets. And here is just a graph where all of these planets that we have discovered, they are shown here. On the x-axis, this is the orbital period. So the number of days they take to finish one orbit around their star. And on the y-axis, it's the planet mass. So comparing to the Earth mass, the mass of the Earth, sorry. So what you see here, so all of these dots are exoplanets, and we have, I also show points of the planet on this planet in our solar system, so that you can compare the kind of exoplanets that we have discovered, how similar or different they are than the planets in our solar system. So we have discovered varieties of planets, hot Jupiter. So again, Jupiter-sized exoplanet orbiting very close to its star. Hot Neptune. So again, Neptune-sized exoplanet orbiting very close to its star. Super Earth. These are planets which are at least, I think they are bigger than Earth, but smaller than Neptune. And we have gas giants. These planets are at least they are more than 5 times bigger than Jupiter. So all of these planets here, all these dots that you see, these planets were discovered through radial velocity in transit. But I want to draw your attention to these red dots. These are the planets that have been directly imaged. And a natural question here is, well, if we know that we have these many exoplanets, if we have 5,000 exoplanets, why we haven't taken images of all of them? Why we have taken images of only planets which are massive? So as I said, gas giants, these are gas giants, massive than Jupiter, and they are very far away from their stars. So if you look here, these planets, like these planets around this area, they are taking 10,000 days to finish their one orbit. So the goal of this talk is to explain why out of 5,000 exoplanets, we have taken images of roughly 50 of them. All right, so here I'm gonna show you again some directly imaged exoplanets. This one I've already shown you. This is another directly imaged planet, bigger than Jupiter, again, lying very far away from its star. When I say very far, what I mean is, so we say the distance between Sun and Earth is 1 AU, 1 astronomical unit. And the distance between Sun and Jupiter is 5 AU. So these planets, when I say they are very far away, what I mean is that they are further than the distance between Sun and Saturn, so further than 10 AU. So with direct imaging of exoplanets, you not only see planets with your own eyes, but you also see the circumstellar material around the star in which these planets form and evolve. So these are, again, real images. At the center, this is the star, which is blocked here. And what you see is are the debris disk. And these are basically the evidence that a planet, or not a planet, a planet or planets might have formed in these systems. So it's very fascinating to see such images in your detector, in your through your telescope. All right. So again, as I said, the question is why out of known 5,000 exoplanets, why we have taken images of only a handful of them? And one of the reason is because star planet system, well, stars are extremely overwhelmingly bright and planets are extremely dim. So exoplanets are roughly 1,000 to 10 billion times fainter than their stars. And if you were to find a firefly sitting somewhere on this lighthouse, and let's say you're looking at this system from thousands of kilometers away, and I ask you to find a firefly around this lighthouse through your telescope, you wouldn't be able to see anything. Why? Because it's so bright. So what you need to do is you turn off the light so that you can see the signal from this little bug. Another way to explain this is if you were to go up in the universe, you go outside of the solar system and you go at 10 parsec away. 10 parsec is 36 light years. So if you were to go 10 parsec away from the solar system, and if you were to look back, the question is, would you be able to see Earth around sun? And the answer is no, because Earth is Earth is 10 billion times fainter than sun, and it's impossible to see it with our naked eyes. So this is exactly what we are trying to do from Earth. We are trying to look up and trying to find the faint signal from exoplanets around other stars, which are really far, far away. So one problem is the contrast is very high. Basically, the stars are extremely bright. That's one problem. So there are ways to tackle this problem. So, for example, during solar eclipse, so as I said, like you need to turn off the lighthouse in order to see a faint signal, right? So a natural example is a solar eclipse. So during solar eclipse, you have the moon comes in between the Earth and the sun. So this is a simulated image. And during the totality, when the moon has completely blocked the sun, during the daytime, you can see planets of our own solar system and other stars as well during the daylight. But only when you have totality, when the moon has completely covered the sun. So 100 years ago, almost 100 years ago, people would have to wait for the solar eclipse to happen so that they could study the corona of the sun, the prominences of the sun. But in 1930s, a French astronomer, Bernard Liot, he discovered something which we call coronagraphs. So a coronagraph is a piece of optic that you put inside your telescope to physically block the light of the star. So in his case, he didn't have to wait for the solar eclipse to happen. He blocked the light of the star by placing an opaque piece of disc at the focal plane of his telescope to block the light of the sun so that he could study the sun whenever he wanted. So here he is looking at the sun during the daylight through his coronagraph. And here it's one of his photographic plate where this black disc is it's a coronagraph, and here you see the corona of the sun. And if you notice here, this is Mercury. So during the daylight, basically, he was able to see planets of our own solar system, in this case, Mercury, during the daylight, basically. So this is what we are trying to do when we look at the stars in the night sky. We want to be able to see such signal around other stars. So Bernard Liot used a very simple coronagraph, which was just it's an opaque disc that he used to block the light of the sun. And what we use today, we have different varieties of complicated coronagraphs because Bernoulli's coronagraph works in our instrument when we want to block the light of the star, but it's not efficient. So we have discovered different kind of coronagraphs to really try to suppress the light of the star that we see. I'm not going to go into detail. I just wanted to just give you an idea that it's coronagraphy is a field in itself. All right, so before I show you how do you actually block the light of the star in the instrument, I want to first explain you how an image of a star is formed in a telescope. So this is a typical reflecting telescope, and this design is a Ritchie-Chrétien design. So you have the light from the universe coming from the left in the image here, and the light basically goes to the primary mirror. This is the mirror which is collecting all the photons, and the light is reflected towards the secondary mirror and then towards the tertiary mirror. So either you can actually put your instrument at the Cassegrain focus, or you can make your light be focused at another point in the observatory, which like a NASMIT platform. So when you look at an image from a telescope, this is what an image of a star looks like. We call it diffraction limited image, or the in other terms, point spread function. So what this means is like this is the best image that you're gonna get from your telescope. The theoretical image, basically. So a diffraction limited image. So the light is basically bent around the edge of the telescope. So the image of the star will be limited only by the diffraction around the pupil. So, all right. So now I want to show you how do you actually block the light of the star using a coronagraph. So here I've done some simulation. So if you assume a simple circular pupil and you take its Fourier transformation in your simulation, you get the image of the star. This is the PSF, right? And the central part is called Airy disk, and the rings around it is called PSF rings. So when you're observing, you know that this is the image of, this is the best image that your telescope can produce. But if you change the shape of the pupil, for example, if you take a complicated pupil like this one, so this is a pupil coming from a 30-meter telescope. So at present on the ground, we have the biggest telescope that we have. They range from 5 meters to 10 meters. And in future, we're gonna actually go bigger. We're gonna develop 30-meter class telescope. So this is just a simulated pupil of a 30-meter class telescope. So if you look at, if you wanna see what is the image of a star, what would be the image of the star if you actually observe the night sky with such a pupil? And this is the diffraction limited image that you're gonna get. And just to give you an example in terms of JWST, so JWST, this is a primary mirror, and there are 18 hexagonals here, and you have a secondary mirror, and these are the arms holding the secondary mirror. So I really like this simulation example shown in one of their papers. So it just shows you the evolution of your PSF, like how the theoretical image of your star will look like if you just change the size, the shape of your telescope pupil. So if you have a circular pupil, so as I showed, you have an airy disk with nice rings around it. If you have a hexagonal pupil, then you're gonna see diffraction spikes. And if you add a secondary mirror, and then if you go from monolithic mirror to hexagonals, and if you add, you know, the spider arms, we call them spider arms. So these are basically the structure, the support structure here, which is holding the secondary mirror. So if you have such a complicated pupil, this is the image of the star that you're gonna see. So a few days ago, I think the JWST has taken its first image of the star. So this is, I think this is the selfie from one of the selfie of the primary mirror itself from one of the cameras. And this is the diffraction limited image coming from JWST. And I hope now you can see by now that this diffraction spikes that you see is because of the structure of the pupil. And if I focus on one region of the sky here, the background star, they are also they also have a similar shape. They all have diffraction spikes, and these comes from the shape of the pupil. And this is a galaxy, by the way, here. All right, so going back to my simulation here. All right, so I'm going to play a video, and here what I'm going to show is, as I said, you have a coronagraph at the center, at the focal plane of your telescope, and you want to block the light of the star. And in this animation, when I'm going to play it, you will see what I'm doing. I have a coronagraph, and I'm just making the star move from left to right. And when the coronagraph is perfectly aligned with the star, theoretically, you should not see any light. So let me just play this video, and when your starlight is aligned with the coronagraph, you can see a planet. But this is simulation, and everything is beautiful in simulation. In real life, it doesn't work. So if you have a circular pupil like this, and if your PSF is less complicated, and if everything is perfect in your system, then when you suppress the light of the star, you can see a planet. But then if you have a realistic pupil, like TMT pupil, then even though your coronagraph suppresses the diffraction effect and suppresses the starlight, but you will always have some residual diffraction. You will always have some residual starlight left behind in your image, and that will obscure the signal from a planet. So you won't be able to see planet signal here. So that's one problem. Second problem is the Earth atmosphere. So when we are observing a star-planet system using the ground-based telescope, the Earth atmosphere acts as a turbulent medium. So when a light is coming from the universe, it travels in straight lines. But when it enters the Earth atmosphere, it encounters layers of different temperature, pressure, different humidity, different wind speed, and that kind of makes the light dance around. So instead of getting a clear, nice PSF, what you see is just a big blur of light moving around. So here, this is a video. The data taken from 8-meter class telescope, the Subaru telescope, and this is how your diffraction limited PSF looks like. It's a mess basically, and it's because the light is really affected through the turbulent medium of the Earth atmosphere. And when you get an image like this, you know that you cannot block any of the starlight. This is just a starlight, star planet light. And if you don't have a stable, nice PSF, you cannot block anything in here. So, yes, so you cannot block anything because you don't have a good image of a star. So how do you tackle that problem then? So we have an amazing technology called adaptive optics, which actually, I like to call it the art of shaping starlight. So using adaptive optics, you can actually undo the effects of the Earth atmosphere, and you can bring back the distorted starlight back to its diffraction limited image, the theoretical image of the star that your telescope is supposed to give you. So adaptive optics, I think I'm gonna I should focus on this image first. So what happens in adaptive optics, it has like two main components, something called deformable mirror and wavefront sensor. So when the light enters through this huge instrument, adaptive optics, what happens is like it goes through an arm of the instrument called wavefront sensor. Wavefront sensor is just a device which senses how much of your starlight is aberrated. And once you have that information, you can actually apply an opposite correction to the deformable mirror. You can tell the deformable mirror to, deformable mirror is just, is basically a reflecting membrane. supported by actuators, and you can actually make the deformable mirror move. You can have very delicate nanometer level movements. So once you know what the amount of aberration caused by the Earth atmosphere, you can actually reshape the starlight by moving that piece of mirror. I'm going to show you in the video, it will be more clear. So an easy way to understand this is when you take shower and when you want to figure out whether the water is too hot or too cold for you, your body is a wavefront sensor. It's sensing the temperature of the water, and your mind is a controller, and your mind basically sends signal to your hands to control the knob and adjust the temperature of the water. So in adaptive optics, what's happening is like wavefront sensors, they sense the aberration present in the star planet image, and controller basically figure out the controller basically send a signal to the deformable mirror, and deformable mirror changes its shape to bring the light back to the straight, to make the light, to straighten up the light basically. So if I show you this video, so let me just pause here. You have the light coming from the inside the telescope. You have this adaptive optic system. This piece here is a deformable mirror, and this is a wavefront sensor. And here, what's going to happen? Some of the light is going to go to the wavefront sensor, and it's going to measure the aberration. Maybe I should wait, because I think right now what it's showing is sorry, okay. So when the light actually enters the adaptive optic system, it goes to the deformable mirror, to the wavefront sensor, and you see the image of the star again, which is just moving and it's all blurry, right? It's because when you have the light that comes from the universe, it's all distorted. So in here, you will see the wavefront of the light in the shape of sort of like potato chips. It should be straight, but it's not straight. It's all distorted. So that information goes to the wavefront sensor, and wavefront sensor then measures the amount of aberration, and the deformable mirror, which is it's a piece of glass basically, which you can distort using actuators, and you can apply the opposite correction, and those potato chips kind of like they straighten out. The wavefront of the light straighten out, and then once the loop is closed, it's a feedback loop. Once the loop is closed, what you get is the diffraction limited image. It's never a perfect diffraction limited image, but this is the goal of adaptive optics is to basically give us the diffraction limited image, the best image, which your telescope is able to produce. So I just thought to show you one example of how a wavefront sensor works. So here is an example again. It's a very famous wavefront sensor called Shack-Hartman wavefront sensor. And what you see here is you have your camera and you have some lenslet array. So when you have the wavefront of light coming in, each of these lenses, they create their own image on the camera. And when everything is, when there is no aberration, all of these dots that you see, they fall at a certain place. That becomes your reference. But if you have distorted wavefront, all of these lenslets array are gonna focus that light, but that light is not gonna fall at the center, just like in your reference. So you can actually, this is just a way to explain you how you can use a wavefront sensor to figure out what is the aberration in your system. So my expertise is basically wavefront sensing. So I develop wavefront sensor for adaptive optics to undo the effects of the Earth atmosphere. All right, so just to remind you a little bit what I've talked about, and I'm sorry if it's too technical. So you have a coronagraph to block the light of the star. But as we have seen, when we look at the star planet system through the Earth atmosphere, everything is blurry. So first, we need an adaptive optic system to correct the light of the star. And then we can actually block the light of the star. So coronagraphy is really the second step. The first step is closing the loop with AO. That's how we talk about. You close the loop with AO and you get the diffraction limited image. So just to show you some real examples from telescopes. So I just want to say one thing. These videos that I'm going to show, they are on sky videos. And by on sky, I mean to say the instrument was at the telescope and we were taking the data from the telescope. So these are on sky videos. It's kind of like saying, going to the telescope and testing our instrument is like saying going to field trip and looking at birds. So I often talk about on sky videos basically is when you are actually at the observatory and observing a star planet system. Anyways, so here's an example of a pupil, telescope pupil, like Subaru pupil. Sorry, Subaru telescope pupil looks like this one. And this is the diffraction limited theoretical PSF. So when you don't have an AO correction, you have already seen how your starlight is all blurred. But once you have an AO correction and the loop is closed, you get the diffraction limited PSF, which looks closer to your theoretical image. When you don't have an AO correction, this is how your star looks like. And this is coming from an 8-meter class telescope. And if in this video, I just want to mention this black dot that you see, it's a coronagraph. So if you don't have an AO system, there's no point in having a coronagraph. Nothing is going to be blocked. Another problem is sometimes your adaptive optics correction is not great. It's doing its job, but it's still not great. And sometimes you get vibration error. You have vibration inside your instrument as well. So it makes your starlight kind of dance around. So it introduced like pointing errors, tip tilt, for example. So sometimes even if you have AO correction, your coronagraph is not aligned with your starlight. So no, you can't really see any planet signal in such an image. And then you have some nights where everything is working and you have adaptive optics providing a great correction. And then you also have your starlight well aligned behind a coronagraph and everything is aligned and doing its job. But still, when you look at a raw frame like that, it's still hard to see a planet in such an image because of this fast moving noise here. And this fast moving error that you see, we call them speckles. So using the ground-based telescopes, you have AO system to correct for the starlight, you have coronagraphs to block the starlight, but still you cannot see planet signals, signal from the planets in your detector like this. And again, the problem is this fast moving random speckle noise, which basically blurs out everything. So before I move on, I just want to show what kind of images, what kind of magic adaptive optics does. So this is a Keck telescope on the summit of Mauna Kea. And when you don't have an AO system, doesn't matter if you have like a 10-meter class telescope, you're going to get a blurred image like this. So this is, I believe it's an image of Neptune. Yes, Neptune, it's written here. So this image is Neptune in our solar system with no adaptive optics. And once you close the loop with AO, then you kind of get to see the details of all the details of a planet. I think this one is for Saturn, no AO and with AO. And this image is again, I think taken from Gemini telescope. Here you're looking at the center of the Milky Way galaxy. When you don't have an AO system, it's really hard to resolve anything. But when you have an AO system, it's doing its magic. But it still doesn't work when you want to try to find faint signal from a planet in direct imaging. So as I said, these speckles, these fast moving speckles are the problem. So here, again, just another way to show you images, raw images coming from a telescope. This data was taken from one of the direct imaging machine called Gemini Planet Imager, this GPI in short. It was at Gemini South Telescope in Chile. And Gemini South is 8-meter class telescope. And even like the Exoplanet imaging machine are giving such raw frames. And you can see again, after the AO correction and after suppressing the starlight, you still have some residuals. So we basically rely on post-processing techniques to subtract out this residual noise. So when you actually take all of these short exposure data from the telescope, you take it home, and then you use fancy and sophisticated post-processing algorithms, then you get an image like this where you can see a planet. But again, any planet which is actually near to its star. So again, planets which are at the distance as Earth, so the planets which are at the distance such as Sun, Jupiter, or Sun, Earth, we won't be able to see all of those planets because they might be hiding behind your coronagraph, or might be well, you won't be able to see those planets with your eyes because of the overwhelming noise of the star light. So we do rely on post-processing techniques, but we see only those planets which are young, self-luminous. They emit their own light, and the ones that are really big, giant, bigger than Jupiter, lying very far away from their star. That's exactly what we are able to see, but we don't see planet signal very close to the star, just because we are not able to really get rid of the starlight because of the AO correction is not perfect. Then you have a lot of vibration problem with your instrument as well. So I just want to give you an idea about how such an instrument looks like. So if you have an instrument which has both adaptive optics and coronagraphy, we call them extreme adaptive optics. So extreme AO. So here is the summit of Mauna Kea, and we have on the big island of Hawaii, and we have at least, I think, 13 telescopes there. And one such telescope is Subaru telescope. This is the inside of the telescope. And this is a control building. So I've actually spent 3 years of my life doing my PhD research at Subaru telescope. And this is the AO system. We are at the NASMET IR platform of the Subaru telescope. Well, these are black boxes now because all the optics is inside. So this is the AO system. This is the exoplanet imaging machine here. And if you open this black box, this is how it looks like. So everything that I talked about, adaptive optics and coronagraphy, that's what it takes to actually do all of that. All right, so I just want to mention what are we actually doing to get rid of this fast-moving error, which is still blocking our view, which is still making us. It's basically one of the problems. The current state of the art. The problem with the current state of the art direct imaging instruments at biggest telescopes on the Earth. These speckles, we still cannot get rid of them. So here in Victoria, we have and we're developing an instrument in the lab, which we call New Earth Lab. And we are trying to exactly solve this problem. So this is the view of the lab at the observatory here. And I'm just going to quickly show you the kind of algorithms we work on to suppress these fast moving speckles in real time. And I'm just going to mention that at present, we are not able to suppress this fast moving light on sky. When we're on sky, we're really plagued by this speckle noise. So here in the lab, I'm not going to talk a lot about it, but here is just like we can control this this lab remotely. So when I joined my job a year ago, I still haven't been to the lab, but I've been working remotely, and we have like written all the software to control all the elements. So here we can simulate star planet on the bench here on the instrument. We can also simulate the turbulence that is created by the Earth atmosphere. We can simulate all of that, and we are working on algorithms to first make sure that the coronagraph is always aligned with the starlight, and also making sure that we are able to suppress this the unwanted residual starlight. So just to give you an overview of what we can do in the lab. So please don't focus on all of these. This may look like this is a lot of information here, but what I just did here, I clicked on tip tilt, which means that I introduced vibration in the instrument, and just focus on this light here, how it's all like moving around. And I'm gonna close the loop of my algorithm, and it's gonna make sure that this light is not moving, it's fixed. And what it's telling me that when it's fixed like that, I'm sensing the aberration in real time, and I'm applying the correction on the deformable mirror, making sure that this light stays stable around this round pupil here. So I'm doing wavefront sensing here. And then we have the algorithm to actually suppress the light of the unwanted light coming from speckles. So I think I've just missed, but when we turn on the loop of that algorithm, we can suppress all of those speckles in real time. So this is something that has never been tested on the sky. So we've been developing this technology here in Victoria, and the idea is to take this on the sky, and then in our language, we say we're digging the dark hole. So we want to dig dark hole in our images, so that, which means that we get rid of all the residual starlight, so that we can have a region in our images which is not polluted by speckles or starlight, the starlight noise, and we can see faint signal from an exoplanet. So again, just to show you, this is an image coming from a telescope, a real raw image coming from an 8-meter class telescope, blurred and affected by starlight noise. And what we want, our aim is to dig a dark hole like that in real time, so that we can see planet images. So I know it was a bit technical, but the idea here is the question I want to remind you, the question was, why out of 5,000 exoplanets we have taken images of only 50 of them? And this is the reason. It's because we are still limited by the technology. We still cannot see clearly. We don't have clear images, and everything is kind of like blurred and messy. At present, these are the telescopes at the biggest telescopes on Mauna Kea in Hawaii, and these are the one in Chile in Southern Hemisphere. So with these current big telescopes, we can only see extrasolar giant planets which are massive than Jupiter, and they lie very far away from their star. And this is the reason why, even with the biggest, largest telescope, we can see only big planets. And the idea is, in near future, when we're going to have ELT, which is extremely large telescopes. So we're going to have TMT, 30-meter telescope, which is being developed by 5 countries, US, Canada, India, Japan, China. And the Europeans have their own telescope. They're kind of like TMT is 30 meters, and I think Europeans ELT is 39 meters, and they have already started constructing their telescope in Chile. So when we're gonna have these telescopes, then we will be able to actually take images of rocky planets, Earth-like planets, basically, or planets which are at the same distance as Sun, Jupiter, or even less than that. All right, so I just have 2 more slides. One slide, the summary. So when we talk about direct imaging of exoplanets, we need high angular resolution. In order to see planets at the scale of our solar system, we need to go bigger. We need to have big telescopes, 30 meters or more. And the planets are really dim. So we use coronagraphs to block the light of the star. We use adaptive optics to shape the light of the star, to bring back the light to the diffraction limited image. And then we use differential imaging techniques to basically suppress the unwanted starlight so that we can see closer to the star. This is my last slide, but I want to just mention one thing. You're going to ask me a question about, well, what JWST is going to do, and what about sending a telescope in space? Yes, there is no Earth atmosphere in space, so you are free of AO system but you still have wavefront aberrations because of the optomechanical vibration. And because of the reaction wheel of the telescope, you're going to have vibration in your system, and it's going to create wavefront aberration, and it's going to spill your light all around, in your images. So even though you don't need an adaptive optic system, but you still have wavefront aberration happening in space telescope. So you still need, you will still have those speckles destroying the image of your planet, basically. So I just want to show a video that you can actually watch later on. It's a JWST video, and JWST basically has direct imaging instrument on board, NIRCam and MIRI. And I'm just going to play this video only for a few seconds, and hopefully you will be able to understand what this video is going to talk about, direct imaging of exoplanets.
In the primary mirror. The MIRI instrument is composed of a camera and an integral field spectrometer, both observing in the mid-infrared between 5 and 28 microns. The optical system of the camera, designed by the French team, is made of 5 mirrors and a filter wheel which selects the infrared radiation. The images are formed on a detector cooled down to a temperature of 7 Kelvin or minus 266 degrees Celsius. The study of exoplanet atmospheres, planets orbiting other stars than the Sun, is one of the major objectives of MIRI. For that purpose, it uses 2 different observing techniques. The first is a new technical innovation called phase mask coronagraphy. The coronagraphs of MIRI consist of a mask located at the entrance of the instrument and a diaphragm placed in the filter wheel. The objective is to attenuate the light of the central star to observe the very weak signal emitted by.
I want to just pause the video here just to show you. This is obviously a simulated image, but this is the final image that you're looking at, and you still see the diffraction coming from the JWST pupil. So you will see the diffraction pattern. This is gonna hide the signal from planets.
Exoplanet, similar to the principle of a solar eclipse.
And I'm going to pause again here just to show you, even like in this video, they show, these planet moving, but then do you notice something here? This all is the residual starlight. It's going to be there even in JWST. With JWST, we're not going to find Earth-like planets. We're going to be looking at planets of the order of what we find in our solar system, and at less than 10 AU. But again, I just wanted to point out that even in this video, few seconds of video, when they talk about the direct imaging instrument on board JWST, you see how even the simulated images, they have starlight spill all over, because even though you don't have an Earth atmosphere up there, but your image quality is not going to be as great as you would think. So I think I'll stop here. Thank you so much for listening, and I'll take questions.
Oh, thanks, Garima. Amy, you are here with us. Excellent. All right.
Yeah. Okay, so I did see a couple come through. So there was some videos that you had up of the AO correction. The question is, what is the scale of the AO correction pictures in RSEC? Yeah.
Oh, I think these are, I need to, I don't have the number, but it's a very small field of view. I'm sorry, I don't have the exact number, but it's a very small field of view, and these images were taken 6-7 years ago.
And one thing, just both on YouTube and in Zoom that I'm seeing in the chat is You explained everything so incredibly well. Thank you so much. Like, I found that just so informative, and it was really clear and easy to understand. So
Oh,
thank you very much.
I was a bit nervous.
Amy?
Ben Dorman has a question that he wanted to ask.
So I'm just trying to understand this differential imaging. I know that in why am I getting host asked me to start my video? Oh, right, yeah, okay. That's what you meant.
Sorry, only if you want.
Oh, right. So yeah, I mean, it reminds me of the technique that photographers use on Earth to take pictures of great buildings like, Buckingham Palace, Taj Mahal, Eiffel Tower, when there's crowded people around. That you want to take this picture, but there's too many people in the way. But the people move all the time, so you can keep on it for a while and then just subtract out the bits that have changed as it moves. Is it rather like that?
Yeah, the differential imaging, the images that I've shown, the directly imaged planet, they all have been post-processed using something called angular differential imaging. So it's exactly, well, similar to what you just mentioned. So these are, in ADI, what happens is like you're looking at the patch of the sky and you let the field rotate, and you make sure that your telescope pupil is fixed on your detector. And when you let that happen, you have when you take like long exposure images, you will see that your planet is moving in all of these images, and then you can kind of like rotate them back, stack them back, and then subtract the mean of all of the images. So you would be just left with planet light, and all of the residuals will subtract out. But then again, this is ADI technique is what's saving us basically. From
amazing. I used to go to AES meetings in the late 80s, and we used to talk about an amazing future where you could actually do some of this stuff. And it's happened.
Another question for you. When you're removing the speckles, do you just take the minimum value of each position, or do the planets disappear as well when you do that?
Oh, so planet light so we have different kind of techniques to suppress those speckles. And forgive me if I'm going to use too many technical words. So one of the technique that we are using in the lab here, we make sure that planet light is not coherent with the starlight. So when that happens, the speckles and the light of the speckle and the starlight, the residual starlight, is not coherent with the planet light. So when we subtract out, we figure out the phase and amplitude of those speckles, and we subtract them. We don't subtract them. We basically get the phase and amplitude of the speckles, and we apply the correction on the deformable mirror to suppress them. And when we do that, planet light is not affected. It's only the speckles and the starlight, just because it's not coherent with the planet light. So planet will stay there. It's just the speckle light which we are correcting.
Able to take away.
I hope I answered that question.
Yeah, I think so. John, does that answer your question? I think so, probably. Another question. How does lower Earth satellites affect the wavefront detection? Is the increase in expected traffic a concern for the project that you're working on?
So when we are actually doing the adaptive optics correction, we are not affected by the wavefront sensing capability, because we are observing bright stars, and it doesn't really affect. It doesn't affect the way we do the wavefront sensing, but it does affect when we are basically taking images. Then yes, we're gonna see the streaks of light. But when it comes to just closing the loop with adaptive optics, it doesn't affect the correction quality.
Right. What are the differences? Like, are there differences when you have a cooler star as compared to a hotter star? Is one or the other easier to see?
Yes. All right. So with direct imaging of exoplanets, we are finding planets around young stars which are really far away, because we don't have a lot of young stars in our neighborhood. And we prefer young stars because the adaptive optics correction is good. So it's just because of what we can presently do. Direct imaging is limited to finding giant planets around young stars. So, but when we talk about radial velocity method or transit methods, they have also their own biases, but these techniques complement each other. But with adaptive optics, we are bound to look at stars which are bright enough for us to see and use that light to do wavefront sensing.
Will Gemini's new extreme AO system, when it comes online, be of any assistance in your work?
Actually, the work that we are doing here in the New Earth Lab, the instrument that I showed you, that actually we're developing for GPI 2.0. So the extreme AO instrument it's going under upgrade. So GPI is gonna go from, it was at Gemini South and now it's gonna go to Gemini North. And so we're delivering this piece of instrument for GPI. Especially what I showed in the last few slides, where we close the loop and then we make the speckles disappear. This is what we're going to deliver to GPI. So yes, it's gonna help GPI at Gemini North in Hawaii to be able to suppress those speckles on sky.
Okay. Is the light from the exoplanets coming from their intrinsic heat or from reflected starlight?
Yes, so this is something I didn't talk about, but yes, you can find exoplanets either through the reflected light or through the thermal emission. So again, it's because of the way our instruments work. We are all the images that I've shown, these are the planets which are self-luminous, emitting their own heat. So we've been observing them in their in thermal emission, basically. Reflected light planets are the one where you're gonna have with the current ground-based instruments, we cannot find reflected light planets, but that's the goal with ELT when it's gonna be online, but we cannot do anything at present. All we do is just look into the thermal emission.
Okay. I'm not seeing any other questions, but I have one of my own. It's a weird one. But you said that where we sit in our own solar system, we wouldn't actually be detectable using the same methods that you're using. So hypothetically, if there was peoples out there somewhere looking back, doing the same thing we're doing, they wouldn't see us.
Well, it depends on what kind of technology they have. Maybe. Yeah, it was just yeah. So when we're gonna have if you want to look closer to a star, we need bigger telescope. So for example, when I said when we're gonna have ELT, so telescopes of the order of 30 meters or more, those are the telescopes that are going to open up that possibility for us to find rocky planets, the planets closer to their star. So we definitely need big telescopes. So if there are people or aliens out there looking back at us, and it will depend on what kind of technology they have. Maybe they have, like, I don't know, 100-meter telescope so that they will be able to resolve us, maybe.
Wonderful. Okay, Lori actually does have another question.
Hi, Garima, thank you very much for everything. This has been really great. I wanted to know who or what group of people thought about the AO system first. Like how long, what's the history of AO?
I see. Okay, I'm gonna try my best, and it's not the complete and best answer. So I think it was the Americans who were using adaptive optics for defense purpose, and it was not open to astronomy or to anybody, basically. So I think it was used for spy satellites, and it was I obviously don't remember the year, but many years ago, it was proposed to use AO system for astronomy purpose. And it was actually the French team which worked on the very first adaptive optics system called Come On. That was the name of it. And so I think it's the French team which made it work on Sky, but it was a technology developed by the US, I think.
I can add a little bit to that.
Please go ahead.
There was actually non-defense work going on I know at University of Hawaii by the Rodiers, the husband and wife team. And so I think where the Defense Department aspect came in mostly was the laser star aspect, the laser guide star. So there was work in astronomy going on separate from the Defense Department in the U.S. There may have been other stuff happening in Europe, but I'm not aware of. But it was really when the laser guide star stuff came available that it really, advanced adaptive optics in astronomy.
But what year are we talking?
We're talking
What years there?
1980s.
1980s. Okay, thank you. Yeah.
Yeah. There may have been stuff going on. We built a very simple adaptive, what you could call adaptive optics system in Victoria in the 1980s for CFHT, and it was HRCam, and it was basically just a simple tip tilt mirror, which is the simplest AO system you can think of. Just adjust the tip, tries to keep the star in one place rather than moving around, so it doesn't correct higher order aberrations. But that was actually built in Victoria and improved the image quality at CFHT. So it was, but like I say, that's really basic AO.
Thank you.
It helps being old once in a while.
And of course, the transit technique was at least partially, if not wholly, invented in Victorian Vancouver, with Gordon Walker and Bruce Campbell and Stevenson Yang in the late 70s. Only Bruce Campbell used hydrogen fluoride, which was a little bit nasty for the reference spectrum. I just wanted to say thank you very much for this presentation. It was every bit as good as recommended by us, and we wish you best of success in your future instrument development. It's going to make a real difference. Thank you.
Thank you. I really appreciate it. Thank you.
So
Thank you.
we're going to go into the Ask an Astronomer section next. Garima, hopefully you're able to stick around as well, as questions sometimes can be answered by a great number of people, and we've got a lot of wonderful people on today as well who might be able to answer. So for Ask an Astronomer, we have our FDAO chair, Ben Dorman, and we have Jason Beeman back again, who's always a popular Ask an Astronomer panelist. So if anyone has any questions to try to stump these guys, or any questions that you're just burning to know related to astronomy, the Hill, history, please just put them in either of the chats, and we'll go from there. So,
I was gonna actually say, I remember studying a little bit about it with Stevenson Yang, the adaptive optics system. And what blew my mind is that it could come down to essentially they're called Zernike polynomials. And it's each order, like as you add more terms like x or x squared, as you just kind of keep going, corrects more and more and more. And we had a question earlier where they were like, hey, what's the main limiting factor other than dim stars don't give you enough light to split enough? But it comes down to computing power, because somebody figured out that it's just math. And yeah, I've been like, I was reading, I was like, oh yeah, it's about adaptive optics. So I quickly looked it up. I was like, Zernike polynomials, I remember those. Horrible things.
So one question is, what is the closest exoplanet to Earth?
Isn't there one in Alpha Centauri? One of those actually has.
Proxima Centauri,
Yeah.
actually. I believe they just discovered another one last It wasn't last week, it was quite very recently.
Mm-hmm.
That's correct. Yeah, it's Proxima
Yeah.
Sun.
Yeah, you
Yeah.
can maybe you can amplify on that, Garima.
Yeah, it's the Proxima Centauri. It's 4 light years away. It's a 3-star system. It's Alpha Centauri, A and B, and Proxima orbiting all these 3 stars orbiting each other. And yes, Proxima Centauri C was found. I don't remember exactly when, but yes, it was discovered. It was found. Yes,
So
that's the nearest one.
Alpha Centauri is quite a bright star. It's slightly brighter than the sun, and Beta also is quite bright. But Proxima is a red dwarf with an incredibly small luminosity. These things are like, you know, 1/2 to 6/10 of the mass of the sun, and they will essentially live for hundreds of billions of years because they shine so faintly that they will never use up their energy, essentially. And these guys, when they had planets around them, they have to be pretty close to warm any, you know, putative aliens. And what you'll see if you look at the list of exoplanets is some of them have really very short periods around their parent stars, like days. So Mercury, by comparison, is 88 days, the closest planet to the sun. But a lot of these exoplanets around red dwarfs are like 3 or 4 days. It's quite, they would be very interesting worlds to live on if you didn't freeze to death.
Or get absolutely pulled apart by magnetic fields or solar storms.
Oh yeah, the other thing about red dwarfs is they have lots of flares.
Yeah, they're kind of angry for not being very nuclearly active. They're very angry little things.
Yeah, so
They just have attitude.
yeah, but you know that the sun has these coronal mass ejections and so forth that are send space weather out to the Earth, where you get beautiful aurorae, but you also get disruption of radio signals and so on. Well, the red dwarfs do that too, only they're, could be 100th as bright as the sun, but their ejections are actually more massive than what comes out of the sun. We don't really know why they are so much more energetic, but yeah, so being close to them is probably not a good idea, despite their relatively faint light.
We have a question from YouTube. So the question is it possible to measure the surface temperature of these planets? And can you kind of explain how that?
Wow, that's not my domain.
I was gonna say, I know there's an equation that you can use to figure out the temperature of a planet, and everybody really likes it because it gives Earth at 25 or something, and it gives Venus the 400 or whatever Venus is at. And it's kind of the one that the public likes to use when, like, oh, we found an exoplanet and it should have water because it's got this nice little temperature for habitable zone. But the problem with that is there's atmospheres on these things, and atmospheres play a really big part in the temperature. It is not 20 degrees if you step outside the Earth into space. No. If the sun is out, it's like 300. You will burn really quickly. If the sun is not out, you will freeze very quickly. It's a big problem. So getting that kind of thing is difficult. But I know there is some equation that floats around every once in a while, and it gives a good idea. You just have to kind of make some assumptions about their atmosphere. So,
but you mentioned that the planets are thermally radiating, not that you can necessarily measure at what temperature, but you at least know that they have a thermal spectrum, right?
Yeah, you can get some. Well, we have taken spectra of some of the directly imaged planets, and you can get information. I just don't know those equations that you use to do that.
Another question here. What's the future look like for exploring exoplanets? development of instruments other than telescope-like instruments to study radiation, etc.?
That's a great question. Well, the future is bright, I would say. I think the JWST is the first telescope which has, for me, I think it's the technological demonstration for direct imaging of instruments in space. And even though like JWST is not going to look at finding rocky planets, NASA has several missions in line. W first, sorry, it's not called W first anymore, my bad. It's Nancy Space Telescope. I'm sorry if I'm not.
Nancy Roman.
Oh, Nancy, yeah, sorry, yes, thank you. Hebex, LUVAR, these kind of the telescopes which are gonna actually focus on finding Earth-like planet. So I think the future is really bright, and we are improving the technology. Really, we really need to actually suppress the wavefront aberration that we see, and there are many teams which are actively working on testing this technology, especially in vacuum chambers, to really use those speckle suppression techniques to clear out the image. So I think it's in future we're gonna send probes to really look for Earth-like planet, take direct images of Earth-like planet, and from ground we are developing. Like for the TMT, there's a concept, something called PSI, Planetary System Imager. So we are actually developing, creating those concepts to be able to look closer and closer to the star when we're going to have these big telescopes coming, at least on the ground.
Another question here is, if you put aside engineering, manufacturing, and the delivery of it, are there thoughts on moon-based telescopes and how they could help advance looking for exoplanets?
That's a great question. That's a great question. Moon has a thin atmosphere, but not as bad as Earth atmosphere. I don't know. I haven't thought about that. It's a great question.
Yeah. Well, I would think your best, like your advantages are less gravity, so you can build bigger mirrors, right? You don't have that kind of limitation, as much as limitation on size, since we're apparently ignoring how hard it would be to send things big to the moon. And then, yeah, with the lower atmosphere, you'd probably get clear images. I know that technically we use the moon as like a radio. You can actually like see the radio reflection in the moon of the Milky Way. There was a fantastic paper maybe 5 years ago, and they were actually imaging the moon in radio, and they were watching the reflection of the Milky Way as it danced across it. So it is a telescope for certain light. It acts like a mirror. So you just got to be smart and clever enough to figure out how to use it.
But one of the things you pointed out was the effect of the telescope structure and engineering itself on the diffraction image, and that, I guess, you have the advantage over atmospheric shimmering, that you can calculate that very well, and therefore any effects of that can be subtracted out. But then you also mentioned the motor and engineering, the fact that the instrument is moving or has engines that make it vibrate and so on, is another big factor in, let's say, JWST versus the ground-based telescopes, where you don't have to worry about the atmosphere, but you do have to worry about the mechanical operation of the telescope.
Yes. Yeah, those, well, you do get wavefront aberration in space telescopes as well. Yeah, it's and I think that helps. Sorry, go ahead.
To the extent that anything you can do anything to improve that on the moon, that might be some thought. I don't know.
Yeah, and the moon isn't technologically active, so it's a lot quieter than the Earth. If you ignore the fact that it still gets hit by rocks every once in a while.
You
so
mean
that's all
seismologically active?
Seismologically inactive, the moon versus the Earth. So like I say, it would just be a little quieter in that front. You'd have less less wobbles, which would help. So I mean, eventually you'd build something so big that would be a problem, right?
I'll
So-
just point out that the cost of JWST would have funded a lot of AO research on the ground. So yeah, so it's not such an easy question to answer, I don't think. And yeah, because putting stuff up in space is not cheap. The moon is going to be even more expensive. Yeah. And you're never going to get a 30-meter telescope up in space or on the moon, not in this century.
In this economy.
So
It's the price
yeah.
of gas. Yeah. Sorry.
So anyways, don't rule out big ground-based telescopes. And we still have a long way to go with AO on the Earth and applying machine learning techniques to wavefront correction and things. So yeah, there's still a lot of development to move this forward on ground-based telescopes. And we have to give something Garima to work on in the future.
I do have a lot of problems to solve.
I was going to ask just one more question. I see that another one has come in. So, but David is going to start his section soon. So I'm just going to ask this one last question, and then I will thank you guys very much. So the question I have is, Garima, you had mentioned that you were working on some research at HAA. How many different research projects go on our hill at any given time?
That's a tricky question for me because I just joined like a year ago and I haven't been to the office yet.
I can give an answer to that.
Please.
It's a large
it's
number.
influence,
It's probably on the order of 30 to 40 projects of different types and sizes. But there's just a lot of really interesting technology work going on up on the hill. So yeah, it's a great place, and I would bring back the history stuff because I mentioned at the beginning the Plaskett report from 1922. Well, Plaskett was working on stuff then. He was working on a new spectrograph for the telescope, and he was not only a scientist and a director manager, but he was a great builder of telescopes and instruments. So the technical instrumentation work happened at Victoria right from the beginning, and it's carried on and it's going strong 100 years later. It's part of our DNA.
So I do see that there are other questions coming in. I'm going to be ending this session here, though. Garima, if you're able to answer some of the questions coming in on Zoom, Jason, I know you're all over. You're all over the YouTube questions. And then if not, if any questions don't get answered, we'll bring them back for the April 16th Star Party. Thank you so much, Garima. As you can tell, people have just loved your topic, loved your talk. Ben and Jason, thank you very much for answering questions as well.
Thanks for having me again.
Thank you.
And I'm going to invite David Lee for the last about 15-20 minutes to tell us about EAA and what we're looking at tonight.
That's great. Thank you very, very much. Garima, thanks again. Just a wonderful description of coronagraphs on AO. I loved it. It was really, really good. So actually tonight we have a couple of offerings. We have some images from the Plaskett and with Dan Posey, and we have some images from Brock Johnson from his home observatory. So let's just start with Dan first.
Okay, so I'm just going to pop my screen up. That was an absolutely fantastic talk. You're going to get tired of hearing that, but I had to at least chime in there because I haven't said anything yet. So we have a few images tonight from the Plaskett. And one of the fun things that we're going to be looking at are the penalties of the atmosphere when it comes to high resolution imaging. But the interesting thing about tonight is that we don't always get to do is we're going to have a blend of both what you could consider EAA, so quick images that aren't terribly well processed, and some more detailed stuff. So let's start with the EAA item first. And this one might not look like much, but it's a really fascinating one from a night that we had on the telescope to generate some images for members of the Astronomical Society as well as public outreach. And we're looking at the Messier 87 galaxy, which is a huge elliptical galaxy out in the constellation of Virgo. Can't remember the distance, but many, many times larger than our own Milky Way. I think that we have something on the order of a couple hundred globular clusters, and this thing has on the order of a couple thousand, and usually globular clusters are a good indication of how large a galaxy is. But this also gives us a look at the extragalactic, or the relativistic jet coming off the center of the black hole in Messier 87, which we were catching in every frame. These were just 30-second shots because the tracking on the plasket was giving a little bit of grief that night. But incredible when you think that it's, oh, I have to do math now. David, we're what, 106 years since the gear was installed, October 1916. So
That sounds about right.
we're coming up on something being long in the tooth, both gear teeth and in age, but pretty incredible that it's tracking this well, unguided 106 years later. And then we get into some of the more processed work from the plasket. So we sat a little bit of time on the Horsehead. And this is where there would be an opportunity for an adaptive optic system. Not that I'm prompting or prodding anybody to try and install one, but an adaptive optic system to help clean up some of the resolution and pull even more out. The plasket's mirror isn't that far off in size. It's 1.8 meters, 72 inches. I think, what, Hubble's, is it 100 or 200? If anybody wants to jump in and free me from my ignorance. But you can do a lot with these mirrors. We're all limited by the atmosphere, though, when we're shooting from a platform that doesn't have adaptive optics. And this is one of the things that we'll likely get a chance to dive into a bit deeper tonight, is the differences between a professional telescope like the plasket and something that an amateur would use, where you can accomplish images like this with an amateur telescope because it's possible to get right down to the resolution image limits of the atmosphere. What's challenging with it is that you have to then spend hours and hours to rival the light grasp of something like the plasket. This is 6 minutes of data, and even on a very big, beefy amateur telescope, you'd probably need between 6 and 10 hours of data to come anywhere close to this. So quite fun stuff. And you can see how this begins to evolve when you look at some deeper shots of Messier 51. So this is commonly known as the Whirlpool Galaxy to amateurs. It's a interacting spiral galaxy up in, it's just off the Big Dipper. I think it's Coma Berenices. But in any case, you can see this incredible depth and richness to the information that we're getting out of the plasket on this frame. This is something like 20 minutes of data. So not very much, but riding as closely as we could to the tracking limits for that evening and pulling out quite a bit of nice, rich detail and information and a lot of depth given the light pollution in Victoria. So we finished out the night with these, and this is where we really get into the fun because these are color images. This is the Black Eye Galaxy, Messier 64, and you have a lot of interesting contrast and color going on. It gets its name because if you're looking at it naked eye with a smaller telescope, there's a dark spot right in the core of the galaxy, and so it was called the Black Eye. But some really lovely richness. This is a false color image. We were using filters from the Sloan Digital Sky Survey filter set, the UGRIS set of filters, and so green was mapped, or G prime was mapped to blue, R prime to green, and I prime, which is kind of bordering the near infrared, into red to shoot this. But it works out because galaxies are are more or less black body emitters, which means that you're able to just shift the rainbow over a little bit and your spectrum over a little bit, and everything will at least partially line up. And then finally, the showpiece from the night, and this is, I would say, probably the most exciting image that we've ever shot off the plasket for this kind of purpose, because it really shows off just what an incredible piece of machinery it is and what you can still do with that equipment, given the light pollution in Victoria. Shooting broadband images without any light pollution filters or any special enhancement isn't easy. And in this case, I was shooting the Hickson 44 Galaxy group, which is actually 4 members. There's a 4th member that's just sitting out of frame here, but we couldn't fit it in. You have an elliptical member up here, an interacting galaxy down here, one of the ARP catalog, and then NGC, I think it's 3190, which is right here. And we caught quite a bit of detail in all of these, but what's incredible is the depth of what we were getting with the telescope for this one. This is the one of those images where I don't think that anybody would ever have the patience or the time to try and rival anything quite like this with an amateur setup, because I tried to do some depth finding on it and find out how deep it went. The Sloan Digital Sky Survey data, and again, anybody jump in if I'm wrong on this, tends to peter out at about 23rd magnitude. And this was punching much deeper than that. So it's likely hovering around 25th, maybe 26th magnitude for some of the fainter background features. But even if you reference against the Hubble image for NGC 3190 here, all of these background features are quite faint, even in that Hubble image, but they're still there. So it was a really fascinating one. Really happy to be able to share and show off some of what that telescope's able to do, and keep building up our library of images for public outreach. But yeah, any questions about any of these before we pass on? I don't want to ramble too long. I know that we have other stuff to share tonight.
Dan, how many images was this?
This last one was our biggest one of the night, and just let me tell you here. As I said, we shot 30-second frames to try and keep the tracking as clean as possible. So it's 30 minutes per filter. So 60 frames per filter. The reason why I took that approach is that it's actually an old amateur trick to get past light pollution. The way that light pollution builds on an image is fairly constant. It's flat, which means, I mean, it changes a bit depending on where the target is in the sky, but it's pretty predictable. And so your signal to noise ratio in a stack increases at the square root of the number of frames that you add in, meaning for us with the light pollution around here, there's not a terrible amount of difference between, say, a 30-second frame and a 1-minute frame in terms of how much depth we go to. We kind of get stopped, particularly in the R and I prime filters, by the light pollution quite quickly. We can only get down to about 20th magnitude. So shooting shorter frames, but more of them, let us slip past the light pollution, because you start to build all of the detail in the galaxies and these other faint background images while keeping the noise from the light pollution about the same. At least it worked in this case. Any other questions?
Okay, well, thanks, Dan, for that. There's going to be more images from the plasket coming up in this season, so look for those. Now we're going to go to the opposite end of the spectrum in terms of telescope size. We're going to go over to Brock Johnson now. His rig's a bit more of an amateur rig, but amazing images. So his approach is a little bit different. He's using one-shot color. So the plasket's more old school, using separate filters for each of the parts of the palette. So, but he's got some tricks up his sleeve as well. So he's using kind of specialty dual band filters for a lot of these images. Yeah, take it over, Brock.
Sure. I assume you can see the first image, the Horsehead Nebula.
Absolutely.
And so I actually didn't really plan it this way, but I forgot that you were showing it. So it worked out well that you were comparing what you'd see with a amateur telescope and the Plaskett. The time that this was actually, I've got 5 hours exposure on this image. So, but it's actually interesting how some of the detail is not that much worse than the Plaskett. As you were saying, the atmosphere is probably the limiting factor. But of course, this is in color with a one-shot color camera and some filters for helping with the contrast and getting rid of light pollution.
I'm just happy that I was that close on the hour estimate of what you would need to come after 6 minutes.
Yeah, 6 minutes.
It's a great shot, Brock.
I need a bigger telescope. This one is Thor's helmet, which is NGC 2359. And it's basically an emission nebula in the center around a Wolf-Rayet star. And it's a really interesting shot. I'd like, it was a little hard to get. It was some of the fainter reddish detail is way harder to get than I kind of figured, but I was overall pretty happy with it. And this one was probably one of the faintest things that I've shot. It's the Witchhead Nebula, and it's basically all just a bunch of dust and gas. So it took quite a bit of processing to get it to look half decent. But this also, actually, this was without a filter. So we had a couple of weeks ago, we had pretty much a new moon and we had a few clear nights. So I went out hoping the light pollution and greenhouses weren't too bad. And I went no filter for a couple of images. And this was one of them.
Brock, this wasn't in an ideal location in the sky either, was it?
No, well, yeah, it's down pretty low. It's sort of below and to the right of Orion. So it's getting pretty down far into the lower part of the atmosphere. So it's behind a lot of wibbly wobbly refractive material. So
you need an AO system.
I need, exactly. I'm just kind of hoping somebody will just say, hey, I've got something here for you. But I don't think that's going to happen. And then as the Milky Way is slowly drifting out of view, so coming in the next few months, we're going to be spending a lot more time staring out of the plane of the galaxy into deeper space. And so this one is Messier 105, which is an elliptical galaxy. I think it's in Leo. And this one I put 7 hours and 54 minutes into. And actually pretty happy at the resolution of some of you can see little red nebula that are within this galaxy. And so that's pretty happy with the level of detail I got with that. This will, of course, been much, much higher in the sky. So the atmosphere is thinner and it's a lot, it's amazing how much clearer everything is when you're pointing towards the zenith as opposed to towards the horizon. But pretty happy with that. And I think I have one more. Yeah, I do. I've got the, this is another one I did without a filter. And this is the Cone Nebula and the Christmas tree cluster up in, I think it's NGC 2264. And this was also, like I said, no filter and about 4 hours of exposure time.
Yeah, I think it's just to the left of Orion.
Yeah.
Yeah.
Yeah. It's
excellent.
Not far from the Rosette Nebula.
Yeah, that's right.
Slightly up and to the left of the Rosette Nebula, which is also to the left and up of Orion itself. So I was pretty happy with that. It's turned out better than I expected it. The color and the texture is pretty amazing. I'd like to get more time on it. See even more. So
amazing.
And I think that's all.
Okay, well, that's really wonderful. Does anybody have any questions for Brock? Otherwise, a big applause for both Dan and Brock. We're going to be bringing you more stuff over the summer. Actually, I think we're probably going to do some lunar stuff soon as well. So, yeah. So there you go.
All
big
right, I
pause.
think- yeah, sorry.
That's okay.
We're just a little delayed. There we go. Hi, Amy. You're on.
And that brings us to 9 o'clock. David, thank you so much. Brock and Dan, that was wonderful. Always really beautiful images. Want to thank everyone for joining us tonight, and Garima again for such a wonderful talk. Just a reminder to mark your calendars for the April 16th Star Party. It's going to have a lunar, it's going to be our lunar night, that one. And a reminder again to check back on Monday afternoon onto our website for information on the prize giveaway for the lunar images. And I look forward to seeing your pictures of the moon come in. Thank you, everyone. Have a great night.
Good night, everybody.
Good night.
Good night.
Right.
Here's all the people.
Okay.
Thanks, Jason.
So have you you haven't stopped it
Yeah,
yet?
good night, guys. Yeah, I did.